Okay, so I'm starting the session. So, is my screen visible to all of you? Am I audible? Okay. So, good evening to all of you. Today, we are going to discuss about the session 8 and about Introductory Organic Chemistry Part 1, which is an NPTEL platform course. And the course instructor are Professor Harina Chakrapani and Professor Neeraja Dashaputre from ISER Pune. And I'm Simran, your PMRF teaching assistant. So till now we have discussed till seven lectures. So I hope it is clear to all of you, all the seven you have seen. And today the topic is alcohols, epoxide, and aromaticity. We are going to talk about these things today. So I hope you guys have watched my videos till week 7. And if you have any query, any doubts regarding that, please feel free to ask me. So is there any doubt till week 7 lecture? Okay, if not, shall I continue with this? Okay. So, guys, today we are going to talk about the reactivity of alcohols, epoxides, and the aromaticity of the compounds. So, here you will get knowledge about the aromaticity, how the compounds are aromatic, anti aromatic, non aromatic. So, these kind of things are we are going to look into it today. So, coming to problem number 1. So, in the problem number 1, they are asking, is the following molecule aromatic, anti aromatic, or non aromatic? So, you have to figure it out that this molecule is aromatic, anti aromatic, or non aromatic. So, before knowing that what is this compound, you first need to know what is aromaticity, anti aromaticity, and non aromaticity. So here is a summary of these things. So there are four things which you have to keep in the mind while answering these kind of questions. That in the aromatic compound, they are usually stable compounds because the condition for aromatic compounds is they should be cyclic, conjugated, and have 4n plus pi electrons. It is requested to all of you, please join on time. Okay. So here I was talking about the aromatic compound. So aromatic compounds have four characteristics, that it should be cyclic, conjugated, have the 4n plus pi 2 pi electrons, and have a flat structure. So basically aromatic and anti-aromatic compounds are differ from each other, having the different number of pi electrons in the system. So when you go through this benzene ring, it has how many pi electrons? Can someone tell? Yeah, 6 pi electrons. So it has 6 pi electrons. So it fits into 4n plus 2 rule. How? That here n is equal to 0 and 4 plus 2 is 6. So you have 6 pi electrons. So here benzene is, that's why aromatic. It has 4n plus 2 electrons. It has a flat structure. It is conjugated and it is cyclic as well. But when you are coming to anti-aromatic compounds, these compounds have 4n pi electrons, which means that here there is no 4n plus 2 pi electron, whereas you will find 4n pi electron. So this is the main distinction between aromatic and anti-aromatic compounds. Rest is same, but the number of pi electrons will vary for aromatic as well as anti-aromatic compound. So when you are coming to this cyclobutadiene, here are 4 pi electrons. There are 4 pi electrons that are present in the cyclobutadiene system. So each double bond correspond to 2 pi electrons. So you have to remember that each double bond corresponds to 2 pi electrons. So that is why we are saying that in the cyclobutadiene you have 4 pi electrons present. So that is why here n is equal to 0 and you will have 4 pi electrons. So here it is anti-aromatic system. So when you are coming to non-aromatic, in the non-aromatic system, and these four criteria are there, but one of the criteria may fail here. It should be, maybe it would not be cyclic, it would not be conjugated, it wouldn't contain any 4n pi or plus 2 electrons, or it is not flat structure. So one of the criteria will fail in non-aromatic compounds. So when you come to the cyclohexatetraene, here the number of pi electrons are 2, 4, 6, and 8. 8 pi electrons are there, which can be anti-aromatic, but here it doesn't have that flat structure. So that is why we are saying that it is not aromatic or anti-aromatic in system. It is non-aromatic. So here it adopts a tub-like structure to be anti-aromatic, because the stability of these compounds are like aromatic are the most stable compounds and anti-aromatics are the usually unstable compounds. Okay. So after having this much in mind, now you can answer this particular compound is aromatic or anti-aromatic. So now can anyone tell me, is it a aromatic, anti-aromatic or non-aromatic compound? Aromatic. So how it is aromatic? Here you have 1 and 2. 2 double bond, that means 4 pi electrons are present in the system, right? But here if you see only double bond, then you will say that it is an anti-aromatic compound. But now you have to look into this negative charge as well. Negative charge means it has two unshared pair of electron present, right? So here because of the presence of this negative charge, it would also add to this 4 pi as 2 electrons. So there 2 electrons are also present. So here you will end up having this 6 pi electrons, right? So because of the presence of 6 pi electrons, and I have told you, when the compound is failing in this particular region, when it is falling in this particular region having 4n plus 2 pi electrons, then it should be aromatic. So first of all you need to know that 4 rule. First rule is it should be cyclic. So here you can say that it is cyclic. Second thing is it is conjugated. This negative charge lone pair of electron is now conjugated into the system. So that is why we are saying that it is also conjugated. So the third entry was it should have 4n plus 2 pi electrons. I have told you that it has 6 pi electrons because 2 plus 2, which is coming from this two double bonds, one two extra electrons are there because of the negative charge. That is why you are ending up having this 6 pi electrons. Now the fourth rule was it should be flat. So this structure, because of the conjugation, it is also flat. So that is why it is obeying all the four rules for being aromatic. So that is why we can say that this compound is aromatic. So this is how we can say that yes, this compound is aromatic in nature. So is it clear to all of you? Any doubts, any queries in this question? Sorry? Did someone say something? Okay. So if it is clear, then I am moving to problem number 2. So it is the aromatic compound. So now coming to the problem number 2. Again, you have to answer whether this compound is aromatic, anti-aromatic, or non-aromatic in the nature. So, any guesses? What could be this compound? Sorry, non-aromatic. Any other answer than non-aromatic? Anti-aromatic. Okay. So one by one, we will look into the aspects that we are talking about. So one of you are saying that it is anti-aromatic, and one is saying that it is non-aromatic. Now, first of all, just tell me, is it a cyclic molecule? Yes, right. It is a cyclic molecule, right? Now coming to the number of pi electrons. How many pi electrons does this compound have? How many pi electrons? 8 pi electrons. So it has 8 pi electrons. So if you are saying that yes, this 8 pi electrons mean that it is anti-aromatic, it is obeying this 4 and pi electron, but now you have to see another criteria as well. See, is it conjugated? Is this compound conjugated? Sorry. Is there? Yes. Yeah. Because as you can see here, this carbon is sp3 hybridized, guys. So that is why, because of the sp3 hybridized carbon, it is not going to be in the conjugation, because you lack one of the negative charge or lone pair of electron, which could be pushes this electron here and which could make this compound a conjugated molecule, but it is not conjugated. That is why we are saying, okay, okay. So coming back to the question, here we have 8 pi electrons. This molecule is cyclic, but it is not conjugated due to the presence of sp3 hybridization carbon. And we have said that we have to follow these four rule to be anti-aromatic or aromatic, right? So when you come to the pi electrons, you thought that it would be anti-aromatic, but now you have to also look at the cyclic, conjugated, and flat rule as well. So here we lacks one of the rule, that is conjugation. So here in the compound there is no conjugation. That is why we are saying that it is non-aromatic. Okay. If the conjugation is there, then your answer would be right, that it is anti-aromatic. But because of the lack of conjugation and presence of this sp3 hybridized carbon, it is non-aromatic. So the correct answer would be, it is non-aromatic. So is it clear to all of you? Any questions? Okay. So if there is no question, then I'm moving forward. Now coming to problem number 3. So in the problem number 3, they are asking what is the major product of the reaction. See, I have in the previous class I have told you about the substitution reactions, addition reactions, right? So if you have recalled that particular set of reactions, then you can answer these questions very easily. So I have put it these questions as an application of that particular class. So here they are asking the major product of the reaction. So what is the reaction? We will be going one by one. So now in the first part they have added methyl chloride. So what happens? We have oxygen here, lone pairs here, alcohol is present in the surrounding, and you have added methyl chloride. Then what will happen? What will happen next? Any guesses, guys? Because these things I have actually explained you in the previous class. Okay. So first of all, you need to know what is methyl chloride, right? To answer this question. So this is methyl chloride. if you have a CH3 group here in the place of R, if this R is CH3, then this molecule is methyl chloride, that is methane sulfonyl chloride. So here what happens, this is a protecting group basically. So whenever you see this methyl chloride, tosyl chloride, TBS chloride or something like that, and you have alcohol in the system, so the main purpose of addition of these molecule is to protect the alcohol. Okay, so here what will happen now? The lone pair of electrons on the alcohol will attack on the sulfur and this Cl will leave out. Now, after having this moiety in hand, the Cl which was left out will abstract a proton from this hydroxy group and you will end up having this protected alcohol. So you will write it as OMS. So what this protection donates is like OMS. So here first of all you have OH, then this OH is going to what? OMS. Because methyl chloride initial was MsCl, Cl is knocking out, so you will left with having only methylene system, methane sulfonyl, right? So this OH is going to OMS, that means it is getting protected only. So first step is the protection of this alcohol only. So in the protection, now if the stereochemistry is mentioned already of the alcohol, you have to note that the stereochemistry here is unchanged. Means here, if the alcohol is above the plane, then after the protection, it will remain above the plane only. If the alcohol is below the plane, it will remain below the plane after the protection. So, stereochemistry does not change in the protections. Only what you have is hydroxyl group is changing to OMS. If instead of methyl chloride, you have tosyl chloride. Tosyl is means that this R group is this paratoluene group. If this R group here is this paratoluene group, then you will say that the protection is tosyl chloride. So here, what happens again? Similar kind of mechanism will go through, and you will end up having a protected alcohol in the system, right? In that case, now this OH will turns into OTS. Instead of OMS, if the protection is tosyl chloride, then you will write it at OTS. So these are some notations which you kept in mind before doing this kind of exercise. So here in first reaction, what is happening? OH is getting converted into OMS. OMS. So is it clear the first step, the mechanism of the first step, how it is going? Okay. Then if it is clear, then now in the first step, you will have substituted alcohol. Now coming to second step, they have added in the subsecondly sodium azide in the system. Now if they have added the sodium azide, now what will happen? Sodium azide, as you have know that this sodium is positively charged and this azide is negatively charged in this system. So basically sodium will get a partial positive charge and the azide will get a partial negative charge. So can anyone tell me what will be the next step? What would this sodium azide do? Yeah, so it would be nucleophilic attack. So here, substitution of this OMS will happen after the nucleophilic attack of this azide. So how this sodium azide will now attack? Can anyone tell me the attack is SN1 or SN2? I have explained this SN1 SN2 in the last class. Those who have not attended, please go to the go to my website. There you will find the YouTube videos, right? So can anyone now tell me if the attack of this azide SN1 or SN2, which pathway it will follow? SN2. Why? Because here as you can see, if OMS will leave out for having SN1 in hand, you will have this positive charge on this carbon, right? This carbon will have a positive charge first of all. So this is a secondary carbocation. And also the sodium azide is a strong nucleophile. So azide will react to your system like this. So first of all, let's say you have this azide. And now what you have is OMS. Right. What is the substitution? Yes, here we have a methyl. Now this as OMS is above the plane and this hydrogen below the plane. So if nucleophilic attack has to happen, if there is SN2 attack, then what will happen? This azide will attack on this particular carbon and OMS leaves out. So now just tell me the stereochemistry of the product which is getting formed. So the product, everyone knows what will happen as OMS is a leaving group. So what you have is N3 in the system, and here you have hydrogen which was present earlier, and here you have a methyl. So now what will be the stereochemistry of this azide group? Can anyone tell me? Inversion of configuration, yes. So here I have told you that in the SN1, what happens? Racemization will happen. Means, first of all, carbocation generation takes place, and carbocation is free. Nucleophile basically is free to attack on the carbocation from above the plane as well as below the plane. So both possibility was there in the case of SN1. So you will get a racemized product. R and S and enantiomer both will form. So here you will get a racemized product. But in the SN2, it is very specific. So SN2 is very specific, and because there is a transition state, that is a penta-coordinated carbon is getting formed, because where from where your leaving group leaves, the nucleophile has to attack opposite of that, right? So nucleophile here, as you can see here, it is attacking from the backside of the leaving group. So here also azide has to attack on this carbon from the backside of this OMS, that is a leaving group. So here also in penta coordinated carbon transition state forms, and what you have here is the inversion of stereochemistry. Basically, opposite stereochemistry will be here for this particular nucleophile. So now, if OMS is leaving out from above the plane as it is a leaving group, and now your nucleophile is adding from opposite side of that particular leaving group. So means opposite side means now you will have a azide below the plane. So here inversion of configuration happens, and this N3 will attack from the below the side. So here what you have is, first of all, you will have a above the plane configuration, and this above the plane configuration at this carbon is going to below the plane. So that is why we are saying that it is getting inverted. So stereochemistry in the case of SN2 is getting inverted. Inverted means if it was R, then it is getting in S. If it was S, then it was getting in R. But in the case of SN1, it is not true. Here, R and S, both enantiomer is forming in equal amount. So that is why in SN1, racemization takes place, and in SN2, what happened? Inversion in the stereochemistry happens. So here OMS is above the plane as a leaving group, so azide will attack from above the below the plane from the opposite side. So now tell me which will be the correct option. Tell me which will be the correct option. Yeah. So So second one will be the correct one, because here azide is attack is taking place from below the plane, and now if the azide is below the plane, then hydrogen will attain a above the plane chemistry. So that is why second is the correct answer. So is it clear to all of you the explanation, or I have to explain it again? If someone has any problem, please feel free to ask. If someone has not recorded or not seen that recorded video for the last lecture or not attended last lecture, then please ask me if you have any problem, any query in this question. Okay, so everyone got the answer, right? Okay, so coming to problem number 4. If everyone is clear with it, then I'm coming to problem number 4. So, going to problem number 4, now they are asking what is the major product of the following reaction. Now, again, you have to tell the major product of the following reaction. So, what is happening? It is basically a ether, and you are treating it with one equivalent of Hi, hydrogen iodide. Okay, so here, if you are treating this ether with one equivalent of hydrogen iodide, so what is this hydrogen iodide? This is like this. So here you will have a partial positive charge at hydrogen and partial negative charge at iodide. So now what will happen? This oxygen has lone pair of electrons, right? So it will take up this proton. Iodide, which in turn will attack nucleophilic in the system. So here after taking up this proton, now what will happen? This is protonated, right? This is protonated. Then I minus has to attack. Now, if I minus has to attack, now it has two possibilities. Either it would attack here and this bond cleaves, or either it would attack on this carbon and this bond cleaves. Right. So based on these two observations, based on these two possibilities, you have these four options. So now, can anyone tell me what will be the correct option? So which pathway this iodide will prefer, one or two? First thing is clear. Hi is there in the system. Then first of all, this oxygen has lone pair of electron. It will get protonate. After the protonation, this I minus has to attack nucleophilic on this carbon number, either on the carbon number 1, either on the carbon number 2. Right? So now what will happen? Iodide, is it attacking on carbon number 1 or carbon number 2? Can anyone tell me? Will iodide prefer to attack on carbon number 1 or carbon number 2? Just think about the products which are getting formed and the stability of that products. One by one you have to answer. Carbon number 1, okay. One someone is saying carbon number 1 and other answer was any other thing? Huh. Okay, okay. Yeah. Actually, I think someone is also wants to say something. Okay, that boy who wants to say something, just say na. Because you guys are both are saying simultaneously, so I'm not getting anything. So the girl is saying that the first carbon, and what about you? What were you saying? Carbon number 2. Okay. So one is saying that carbon number 1 is attacked by iodine, and another one is saying that carbon number 2 was attacked by iodine. Okay. So, guys, first of all, I have told you that products you have to imagine. So, if carbon number 1 is getting attacked by iodine, then what will happen? The bond is breaking here. So, there is a carbocation which is here, and you will left up with this moiety and a alcohol, right? So this was the product, and here obviously iodine is getting attached. So this was the product for carbon number 1. So now I want to write for carbon number 2. Then what will be the product? Here you will have this OH, and here you will have this iodine attached, right? Yeah. So now, in both the cases, in the case 1, carbon number 1, the positive charge, the carbocation which is getting generated is here, right? But if you see that the positive charge which is getting created here, now tell me which one is stabilized, this carbocation or this carbocation? Tertiary. See, tertiary carbocation is stable because here we have talked about aromatic, anti-aromatic thing, right? So here what will happen? Guys, please mute your mic. Can you please mute your mic? Okay. Fine. Okay, here the tertiary carbocation is more stable. Why? If you see here in the case of this, I have told you about aromatic, anti-aromatic, non-aromatic compound. So what is this? This is 2 and 4. It would be anti-aromatic, right? So because yeah, because it is an anti-aromatic compound, so the stability of this anti-aromatic compound are very less. If there is a negative charge on this particular carbon, then it would become a aromatic system. So it will prefer, this cyclopentadiene will prefer a negative charge at this sp3 carbon rather than a positive charge, because positive charge will make it as anti-aromatic and negative charge will make it as aromatic. So aromatic system is more stable than anti-aromatic system. So that is why we are saying here that this carbocation, the tertiary one, is more stable than this particular cyclopentadienyl carbocation. So here, that is why the formation of carbocation prefer this way, and iodide will attack on this particular carbon number 1 rather than carbon number 2. Is it clear to all of you? Okay. So if it is clear, what will be the correct option then? 4. So option number 4th will be the correct one. So here, because I'm just repeating myself again, so here what is happening, first of all you are treating this particular ether with one equivalent of Hi. Then what happens, this ether, as it has a lone pair of electrons on oxygen, this oxygen will attack on hydrogen and will give you a protonated oxygen. So the protonated one, now iodide, as it is in the it is present in the system, this I minus has two options, either to attack carbon number 2, either to attack carbon number 1. So it will prefer to attack carbon number 1 because the carbocation which will be generating after the cleavage of this 1 and O bond, then you will have a more stable carbocation in the system, that is tertiary carbocation. And if this I minus will attack on this carbon number 2, then you will have a carbocation which is anti-aromatic in the nature. So that is why instead of going to carbon number 2, the iodide prefer attacks on carbon number 1. So if it is attacking on carbon number 1, then what you will have is the this particular compound in the system. So it will be the product for your reaction. So is it clear? The option number 4 is the correct one. So any queries, any problem in this question? Iodine is a bulky group. Okay. Okay, okay. So you are thinking according to the atomic radius, right? So if we think according to atomic radius, that I minus will effectively attack on this particular carbon number 2 rather than carbon number 4. But actually here this I minus atomic radius will not be playing any role, because here also you will have this system that is a cyclic system. So here bulkiness you cannot record either this particular tertiary butyl group is more bulky or this is more bulky, because you also have this cyclic system in hand which is also considering, which is also a bulky group. So if I minus has to attack, it would feel same kind of interaction while attacking on this system and attacking on this system. So the carbocation, as I have told you, it is a planar system, carbocation, right? So here the attack for I minus is more or less similar, and atomic radius doesn't play a role here, because see, if you say that it is a bulky group, then you cannot reject this group as a bulky group, because here also you have five carbons and the aromatic ring as well. So here it is an anti-aromatic ring, and here this is 3 methyl group, but bulkiness is altogether similar to both of them. So that is why you cannot consider this iodide atomic radius here. Instead, you will consider the stability of the carbocation. So you have to consider the stability of the carbocation, which is more stable, and there only the I minus will attack, which is more stable carbocation. Because attacking of I minus is a secondary thing. Generation of positive charge, the generation of the carbocation is the primary thing which is happening in the reaction, right? So the attack of I minus is a secondary thing. So the stability in the first step is important here. So first step is generation of the carbocation. So now here you have to see which is more stable, the carbocation which is more stable. And then only the second step comes into the picture, that is the I minus attack, right? So here atomic radius really not play an important role here. So is it clear to you? Okay. So I hope it is clear to you. If not, then please ask me. Uh, and I cannot say in the next lecture because it is the last lecture for this particular course. So you can ask me on the YouTube platform. Okay. So now, if it is clear, the problem number 4, shall I proceed to problem number 5 then? Okay. So here in the problem number 5, see, I have actually explained you the elimination, substitution, everything. So that's why I am just keeping these kind of problem here. So to just brush up your knowledge, what you have gained last in the last to last lecture or whatever it is. So here you will brush up all the things what you have learned till now. So now in the problem number 5, they are asking identify the major product of this reaction. Again, you have to identify the major products. So now here in the first step, they are treating it with methanol and sodium methoxide. So guys, I have told you in the previous class that what will happen in the system if you have a very strong base in the system, sodium methoxide and ethanol. So here it is a very strong base. Then what will it will do? The person who has attended the last lecture will definitely know the answer. Yeah, elimination. Very good. So here, if you have a very strong base in the system, that is sodium methoxide, and correspondingly this methanol is here. So it will undergo the elimination reaction rather than the substitution one, because substitution in the substitution your nucleophile should be very powerful, right? But here your base is much stronger. So here it will act as a base rather than a nucleophile. So here elimination will happen in the system rather than the substitution. So what will happen now? From where the elimination happens? So this base will abstract one of the acidic proton. So either the hydrogen 1 or either hydrogen number 2. Two possibilities are there for the abstraction. So now what will be the hydrogen which would be abstracted by this base? Can anyone tell me, is it the H1 or H2? H1. See, for elimination reaction to take place, if this negative charge is getting generated after the abstraction of this proton at this carbon, will the elimination takes place? Because here Br, your bromo, that is a leaving group. For elimination, I have told you, for the E2 elimination, I have told you that the leaving group and the proton should be anti to each other. That is, it should be anti-periplanar to each other. The leaving group and the proton, which is abstracted by the base, should be anti-periplanar to each other. It is the rule for E2 elimination. But if you abstract this H1 from this position, if you abstract this H1 and this negative charge is getting formed, will it leads to any kind of elimination, do you think? Because here this hydrogen H2 is only present anti to this bromo, and after the elimination and generation of this carbon ion at this position, it will go here and this bromo leaves out, right? The generation of the carbon ion at carbon number 1 is not giving you any kind of alkene or any kind of elimination reaction. Here, if the carbon ion is getting generated, then again it will trap proton from this methanol and it will again hydrogenate. So there is no fate for this particular carbon ion to get generated at carbon number 1. But if you generate a carbon ion at carbon number 2, then what will happen? Here this carbon ion will move forward and this Br leaves out. So now this kind of elimination can happen only if the carbon ion is generated at carbon number 2. So this is clear that the carbon ion is generating at carbon number 2, right? So now you also have to assign the stereochemistry for this particular thing. So here, if this alkene is getting generated, so I have told you that E2 elimination, H and Br should be anti. So here this methyl is present at this position and this is hydrogen, right? And this is actually this. So this hydrogen and this Br is already present anti to each other. That is why you don't have to rotate the bonds. So here you will have this kind of elimination, and what you will end up with, see, what was the stereochemistry, it will remain as it is because you have not moved any of the bond, you just have eliminated this HBr as it is. So what was the stereochemistry previously, that this 2 methyl was trans to each other, it will remain trans to each other only, right? No change in the stereochemistry will observe because it is already present anti to each other, this H and Br, and thus there is no need to orient that particular bond, and you will end up having the similar stereochemistry which was there in the reactant. So product will also have the same stereochemistry. So first is sorted. So you will end up having elimination and this alkene you will got. So is the first step clear to all of you? How this alkene is generated, how the stereochemistry is there, how the elimination is happening. Is it clear? The first step I'm talking about. Okay. Then if it is clear, then coming to step number 2, that they have added MCPBA in the reaction. What do you mean by MCPBA? It is metachloroperbenzoic acid. So now you have added metachloroperbenzoic acid. When you are having this alkene in hand, you have added what? MCPBA. This MCPBA was added now. So what is the structure of MCPBA and what it will do? You have to see now. So this was the A2 elimination mechanism. I have told you that base will abstract this and this will go like this. So it is the A2 elimination. So you can refer this, those who haven't attended the last lecture. So now what will MCPBA do? What is the structure now? So this is what MCPBA looks like. This is metachloro per benzoic acid. Per means you will have two oxygen here because there is peroxide linkage, right? So here this is the structure for my MCPBA. And now what will happen? See, this alkene will form a transition state with this MCPBA. Here you will have a coordination with this oxygen of this peroxide linkage, and you will end up having this peroxybenzoic acid, benzoic acid in the system. So now one of the oxygen from this peroxide linkage will get transferred to this alkene bond. So here nothing is happening. This alkene is just taking one of the oxygen from the peroxide linkage. So this is how you will end up having this epoxide in hand. So one of the oxygen from the peroxide linkage is donated to this alkene, and what will happen? You will end up having a epoxide, and the byproduct was the metachlorobenzoic acid. So you, instead of MCPBA, you will have this particular benzoic acid in the system as a byproduct, and the peroxide linkage, one of the oxygen is getting donated to this alkene to give you this epoxide. So now you have to figure it out what would be the stereochemistry at the ends of this epoxide. So this is the particular mechanism of how this epoxide ring is getting generated. So after have looking this mechanism, you can say that yes, this alkene bond is converting into a epoxide linkage. So this is what you will get. So now tell me, based on this particular mechanism and based on the this product what you have, what could be the possible option of the product which could be possible here? So here, which would be the particular conformation of the product which is present? So is it the option number 1, 2, 3, and 4? See, 3 and 4 doesn't give you the epoxide linkage, so it is getting eliminated, although, right? So you have to answer in between 1 and 2 only. So what could be the possible product? Any guesses? Option 1. Because in whole the process, the stereochemistry is not going to change anyway, right? What was the stereochemistry previously in the reactant? It will remain the same with the product as well. So here, in the first case, what you have seen is the elimination, which was E2 elimination, and then after having this alkene in hand, you will treated with MCPBA. And what will MCPBA do? The peroxide linkage, one of the oxygen will transmitted to this alkene bond to give you the epoxide, and this epoxide will be having the same stereochemistry which was there in the reactant. So that in the reactant, the alkene was trans, then the epoxide also having the trans methyl present in the system rather than the cis methyl. So these two methyl should be trans, right? So option number 1 will be the correct one. So it is the correct option. So is it okay to all of you? Did you understand what is happening in the reaction? Any doubts? What happened? Any doubts? So if there is no doubt, then I'm moving forward to problem number 6. Coming to problem number 6. So what stereoisomer do the following reaction form? So now they're asking straightforward what is the stereoisomer that would be formed in this particular reaction. So again, first of all, the first reaction is methyl chloride and pyridine. Then what will happen now? Tell me, in the first step, what is happening? Yeah. OH is going to be protected by methyl chloride. The similar mechanism is happening here. First of all, oxygen lone pair will attack on the sulfur of methane sulfuryl chloride, and this Cl will knock out. Then this Cl or the pyridine, if there is pyridine that is present in the system, this pyridine will take up this proton. It is a base, so it will take up this proton, and you will have this protected alcohol in hand, right? So first step is clear to all of you that yes, here what you will have is this OMS. Now the stereochemistry will not change anyway because I've told you that protections doesn't change stereochemistry. So this is what you will have now. Now the second step is addition of this methoxide. This methoxide ion is getting added. So now just tell me, in all the cases this methoxide is getting added and this OMS is there. So what could be the attack of this, what could be the nature of the attack of this methoxide, whether it is above the plane, below the plane, or what is happening? Below the plane. Okay, you are saying below the plane. So here this methoxide has to attack according, anyone is saying any other answer with other than below the plane? Okay, so guys, what is happening again? We have this OMS as the leaving group, and what is the kind of substitution which is happening here? SN2, right? Again SN2 is happening. I have told you in SN2 what you will have is inversion in the configuration, right? Yeah, inversion. You will have a inversion in the configuration. What you mean by inversion? That stereochemistry will change. If it was previously R, then it is going to S. If it was previously S, then it is going into R. So here inversion is happening. So here your leaving group is below the plane. Then just tell me, if nucleophile has to attack, then what will be the position of attack? Either above or below the plane. Your leaving group is below the plane. A nucleophile has to attack on this carbon. Then what will be the position of attacking? Either above the plane or below the plane? Yeah. So here we have the stereochemistry that should be opposite to this OMS stereochemistry, because in the SN2 I have told you that the attack is going to take place from the back side of the leaving group. So from the back side of the leaving group means it is happening from opposite side of the leaving group. So here leaving group is OMS. So now you will have the attack of nucleophile from above the plane, and OMS is leaving from below the plane. So now you will end up having what? SN2 substitution product in which your methyl is above the plane and your nucleophile is also above the plane. Your nucleophile, and this is methyl. So now tell me what is the correct option? Yes, option number C is the correct one. So how it is correct? Because here the stereochemistry of this methyl is actually fixed, right? It is not going to change because you are not doing anything on this particular carbon. You are just changing the things at this carbon. So now in the first step, first of all, the missile protection will happen. The OH is getting protected. Why this OH is getting protected? Why not this first step is eliminated, guys? And why not the second step is directly do on this particular alcohol? Can anyone tell me why we are protecting this alcohol? Why there is a need to protect the alcohol and then do the SN2 reaction? Can we do the direct SN2 reaction on this alcohol? Can anyone tell me? Sorry. Actually, it is not the case. Here, what is happening? I am just trying to ask you that if I have this alcohol in the system and I am eliminating this first step, right? Eliminating. And I have to just attack this methoxide as SN2, right? As SN2, I have to attack it. So it is a nucleophile, it is going to attack here. Then is it possible that this directly will attack on this carbon and OH leaves out? Is it possible? Yes. Actually, OH group is not easily removed. It's actually is not a leaving group. OH is not at all a leaving group because OH. So here OH minus is not behaving as a leaving group, and it is a very bad leaving group. That is why we are making it a more good leaving group, and that's why we are protecting. Yeah. So that is why we're protecting it with different protections. Right. So that is why we are protecting it with different protections to make it a good leaving group, and then we are doing the SN2 reaction on it. Direct SN2 reaction on this particular OH is not possible actually. It's not because OH is not a good leaving group, right? So here, if you come across any of the reaction in which OH is directly replacing into a Br, can any one of you tell me the reaction in which OH is replacing into Br and OH is behaving as a leaving group? Any reaction? See, there is a reaction known as Appel reaction, right? So in that also, OH is not directly leaving because there also SN2 reaction is happening, but you are using some different things like CBr4 and PPH3 to make this OH as a good leaving group. Again, it will form a bond with triphenylphosphine and will form a phosphine oxide, and then the positive charge that is getting generated on the carbon then is trapped by Br minus, right? If you have come across this Appel reaction, then you can clearly distinguish why we need to actually have a protection here. Someone has any problem? I will tell you the reference book. Actually, you can prefer Claydon because Claydon is a very good book, and also the language is very simple. So you can refer that Claydon book. It is very simple for you to understand the basics. So here, I was talking about the Apple reaction. So here, if someone knows about the Apple reaction, then you can clearly visualize what I'm talking about. If you don't know what is Apple reaction, then just go do the Google and you will get to know. There also, you will make the alcohol good leaving group, and then the SN2 reaction will happen by the Br as a nucleophile. Here also the similar concept is arising here, that first of all you are making the OH a good leaving group, and then the nucleophilic attack is happening, right? So it is a homework for you guys. So just read about the Apple reaction and you will relate with this. Okay. So is it clear how the option number C is the correct one? Any doubts? Any problem in this question? Going to problem number 7. Then I'm going to problem number 7. So here in the problem number 7, What they're asking in the yeah, yeah, ask me what happened. If you apply a very strong base, is it possible to what? Okay. See, if you apply a strong base, just let's say that you are applying a sodium hydride. Sodium hydride is a very strong base. Okay. So if just forget about the sequence of reaction and you are saying that if we are applying a strong base, then what happened, right? See, if you are applying a strong base, then what happened? This OH proton is getting abstracted. Now this OH is going to form this O minus. This is all what is happening if you are applying a strong base. There is no nucleophilic attack that would be possible here by the base. So if the strong base is applied, then this OH minus, as the hydrogen of this OH is very acidic, so that is why it will take up the proton and you will end up having this O minus in hand. And if you are using any of the solvent that is protic, then again this O minus will abstract the proton of that particular solvent and again OH will generate. So this is a equilibrium kind of situation which will happen, right? If you treat with a strong base, so there is no basically there is no substitution of this base will happen and this OH leave out. It is not going to happen anyway. If you are treating it with a strong base, a weak base, doesn't matter, because there is a acidic proton. The strong base will take up that proton and will quench the reaction only. Nothing will happen next, right? So this is how it will go. So is it clear now? Okay. So I hope it is clear to all of you. Now I'm going to problem number 7. So now going to problem number 7. The seventh question is asking, in the given reaction, choose the correct option for products. So they are actually giving you the products A and B, and they are saying that choose the correct option. So these are the four options you have to choose. Sorry, SNI. Okay, just don't be in a very much hurry. You will see. Okay. So here, what will happen now? First of all, they have actually given you the products. They already have given you the product. Now you have to answer which is the correct option, right? So now, first of all, going to the mechanism of this question. Can you please mute your mic? Yeah, thank you. So here, you have to first of all go through the mechanism of this reaction. What is happening? What is happening? This alcohol and this thionyl chloride, and you have pyridine. You have pyridine in the system, right? Pyridine. So this is the short form for pyridine. So here, pyridine is a base. Pyridine is a base. So what will pyridine do if you have alcohol in the system? What will a base do? Can anyone tell me what will a base do? First of all, if you have alcohol in the system and you are adding a base, just now I have explained, it will take up the proton and it will make this a good nucleophile. It will make this oxygen a very good nucleophile. So that is why we are adding a base here to accelerate the reaction. So now, if you are first of all making it a nucleophile and you have thionyl chloride, that is SOCl2, which looks like this. Now this negative charge will attack on the sulfur, and this bond goes here. This oxyanion will get formed. So now this is the tetrahedral intermediate which is getting formed now. And what will happen? This O minus again come down, and one of the Cl group will knock out. Again, this pyridine in the system can take up this proton. Pyridine can take up this proton. Because base is present, right? So that is why this oxygen will not be in the protonated form. So this proton will take up by the pyridine, and again the Cl minus, which is knocking out by the thionyl group, will attack on this particular system. So this Cl minus will again attack on the carbon, and you will end up having this whole thing out. That means now pyridine is taking the H, Cl is going out. What means by that it is having a HCl in the system as a byproduct, right? And what also you have is this SO2, this SO2 fragment, which is coming from here. So you will have this SO2. SO2 is a gas, and HCl is also a gas. So they are knocking out from the system, and what you have is a chlorinated product. So now coming to the stereochemistry, guys. So here this is the particular mechanism what is happening. First of all, pyridine will take up a proton from this alcohol. Carbon ion is getting generated. This carbon ion then attack on the sulfur, and this oxyanion will come down to cleave this Cl minus. Then the Cl minus, which is getting liberated in the system, will again attack on the carbon, and this leaving group leaves out. So basically this group is acting as a leaving group here, this whole group. Okay, so this will leave out. So what is happening next is this Cl minus. What you have to consider here is this Cl minus attack is happening from opposite side, right? Opposite side of the leaving group. It is basically again a similar kind of SN2 reaction which is happening here, because your it is not actually SN2, it is SNI, but still the similar kind of approach was there, because here also this nucleophile is attacking from the backside of the leaving group. So here this whole molecule is acting as a leaving group, this whole system, and your nucleophile is attacking from opposite side of the leaving group. So that is why you are having this chlorinated form in wedge, in below the plane, and here the alcohol was initially at the wedge. So there is another kind of thing here also. You are making this OH what a good leaving group, and then only this nucleophilic substitution will takes place, right? So this is how it works. So is this mechanism clear to all of you what is happening here? Okay. If this mechanism is clear to all of you, then now coming to the question. So now they are claiming that the stereochemistry of this alcohol is above the plane. So what will be the stereochemistry of the product which is getting formed? So what could be the answer? See, you have four options. They are saying that 1:1 mixture of A and B will form, an enantiomeric mixture of A and B will form, only A will form, or only B will form. So what could be the possible option? Any guesses? I have showed you the mechanism, I have showed you what is happening. Then just tell me if the products is could be A or B, then what statement is right? Sorry, can you repeat once? Yeah. Only B is the product. Why? Because there is only one possibility for the attack of Cl minus, because it is a SN2 reaction. I have told you that it is very specific reaction. It is not like SN1 where you will have both the enantiomers in the hand, but here you will end up having only one enantiomer as a product. So that is why if you have alcohol which is having a above the plane stereochemistry, then the product which is getting formed in exclusively is the product where the stereochemistry of the nucleophile here is Cl minus, the nucleophile is, so nucleophile stereochemistry should be below the plane, right? Because the attack of nucleophile is happening from the backside of the leaving group. So the opposite, the inversion in the stereochemistry should be there. So that is why the fourth option will be the correct one, that is only B, that is here this B is only the product which is getting formed in the reaction. So is it clear to all of you this much? Any doubts, any queries in this reaction? Any queries, guys? Okay, if not, then I'm going to problem number 8. I hope there is no problem in the previous question. So, problem number 8 now. So, which compound is the most reactive towards dehydration in HCl? Why you people are joining this much late? So now the question is saying which is the most reactive species toward the dehydration in HCl. Dehydration is HCl. If you are treating these compounds with HCl, then what will happen? Can anyone tell me if I am treating this alcohol with HCl? So first of all, what is happening? If I treat, yeah, yeah, very good. So it is getting protonated. So this alcohol, oxygen is taking this lone pair of electron and this OH is getting protonated, right? So now they are saying that towards the dehydration. Dehydration means loss of water molecule. So here you are having a loss of water molecule. So if you lost this particular H2O molecule, what you will have this? There is a positive charge that is getting generated at CH2, right? Yeah, carbocation. So there is a carbocation which is getting generated at each of the carbon after dehydration. I am writing, right? So after dehydration. So this is the position of the carbon which is getting the carbocation generated after the dehydration in HCl, right? So now you have to compare the stability of the carbocations to know that which is the most reactive. So now just tell me which will be the most reactive for this dehydration. The one species which is having the most stable carbocation, right? The stable carbocation only will now wants to basically dehydrate in this HCl condition, right? So you now have to figure it out that which is the most stable carbocation, because if the carbocation is most stable, then only that will wants to be dehydrated in that HCl condition, because it can actually stabilize this carbocation, right? So just tell me, in among these four, what could be the most stable carbocation species? Four. So here, someone is saying that this last one, and someone is saying that the second last. So one by one, we will go through it. Okay. So now in the first, see in the first case, this carbocation is stabilized. Have you heard about the benzylic carbocation? So this benzylic carbocation, which is generated at this position, here it is the benzylic carbocation. And guys, benzylic carbocation and allylic carbocation. What do you mean by allylic carbocation? This is This is the yeah, yeah. So there is a rule, a thumb rule, that benzylic carbocation, allylic carbocation is more stable than tertiary carbocation, secondary carbocation, and primary carbocation. So this is a, if it is allylic and the first one is benzylic, then it would be highly, this is moreover similar, highly stabilized than tertiary, then secondary, and then primary, right? So this is the reactivity order. So this is basically the stability order looks like. So now if you have any of these system in the hand, then you can consider that it is more stable than tertiary, secondary, and primary carbocation. So here you have one of the system, that is benzylic carbocation. So you have now seen that this benzylic is way more stabilized than tertiary and secondary carbocation. So now coming to this part number 2. Now what is this kind of cation? Is it secondary, tertiary, primary? What is it? The second option is, what is the cation? Primary. Right. So it is a primary carbocation. Coming to option number 3, what is it? Secondary carbocation, right? Again, it is secondary carbocation. This much clear to all of you. I have assigned the carbocation stability order according to this. Is it clear how it is primary, how it is secondary? Okay, if it is clear, then now I have told you that you have to assign the most stable carbocationic species. Guys, if you see, this secondary cation is also a benzylic carbocation. Is it so? Can anyone see this? How it is benzylic? This carbocation. What do you mean by benzylic carbocation? If it is directly attached to the benzene ring, the carbon having the positive charge, then it is known as the benzylic carbocation. So in option 1 and option number 3, you have both benzylic carbocation, and the option number 2nd and 3rd is secondary and primary, right? So just tell me if you have to assign the stability order in among these two, because now I have told you that benzylic is more stable than tertiary, secondary, and primary. So this second option and fourth option is getting neglected because there are species that are more stable than this secondary and fourth. So both are benzylic carbocation. Then just tell me, in first or three, which could be the most stable carbocation? Third one. Because the positive charge here is stabilized by the benzylic species, fair enough. But you have a methyl group also present here. So what will this methyl group do? It is having a electron releasing. Yeah, yeah, it is electron releasing group. So that is why it is stabilizing your positive charge very much. So here, this is a benzylic cation, but it is primary benzylic cation. But this is the secondary benzylic carbocation. That is why it is much more stabilized due to the presence of methyl, which is electron releasing in nature, and thus it will stabilize your positive charge much more than the first one. So that is why the correct option will be option number 3. So it will give the most reactive affinity towards the dehydration in the presence of HCl. So is it clear to all of you the answer? Any doubts? Actually, you can see according to the hyperconjugation structure as well. If you write the hyperconjugation structures now, you will find that this particular benzylic species is actually stabilizing the particular carbocation. You need to actually write the hyperconjugation structure, because if you say that tertiary is more stable than secondary and primary, you say this based on hyperconjugation, right? Based on inductive effect and the hyperconjugation effect. So that here also the similar line is there. There is more hyperconjugation structure which is present in the benzylic form rather than the tertiary, secondary, and primary. So for that hyperconjugation structures, actually you need to write that. Okay. So according to a hyperconjugation only, this positive charge is stabilizing by the benzene ring. It is not the phenyl ring which is getting stabilized by this positive charge. It is only the benzene ring which is giving the extra stability to this positive charge because of the hyperconjugation structure, which is possible in the case of benzene, but it is not possible in the case of phenyl ring due to the aromaticity. Okay. Is it clear? Yeah, sp2 hybridized, but the thing is, see, if you have to see here, there is a significant conjugation which is present, and there is a electron delocalization, right? So that is why, due to it is having electron density and it is delocalizing in the system, you can say that it is more electron rich than the phenyl ring. Is it right? Benzene ring is more electron rich than the phenyl ring. So if it Yeah. So if it is more electron rich, it is stabilizing this positive charge way more than this phenyl ring. And you have to write the hyperconjugation and the inductive effect. These two concepts are there only to stabilize the system actually. So you just need to go through that particular hybridizations and the hyperconjugation and all these things, inductive effect, resonance effect, mesomeric effect. So these things, just go into the basics. I think Clayton has these things, so you can refer those things and can read out there. Okay. So now can I move forward? Okay. Thank you. So now coming to problem number 9. So guys, we will quickly discuss about these questions now. So here what is happening in the problem number 9, they are asking, in the given reaction the structure second will be. Now you have to assign the structure second. So for assigning structure second, you need to assign structure first of all. So now tell me what is happening in the first step. Yeah, tosylation of the OH group. So tosylation is what happening in this particular reaction. So I've told you, if you have replaced with the tosyl group, then you will have a notation that is OTS. So how tosylation is happening? This is the tosyl chloride. This is alcohol. Now you have pyridine in the system. What will pyridine do? Pyridine will make this OH a better nucleophile. It will take up this proton and make this O as O minus. It will make it as a better nucleophile, and this O minus will then attack on the sulfur of this sulfonyl, and the Cl minus leaves out to give you this moiety. Now instead of triethylamine, this is a base also, but you have added in the system pyridine. So again pyridine will abstract this proton of this hydroxy and a cation, and you will end up having this pH OTS in the system. That is the protected alcohol basically. You need to worry about this moiety only. So this is how the tosyl protection is taking place with this OH. Now they have added sodium hydroxide. Now what will happen? Sodium hydroxide is a strong base. Now strong base will deprotonate the acidic proton. So now just tell me, if you have first as this. First is this, right? First is this after tosylation. Then just tell me, if it is a strong base, which proton it should abstract, which is the acidic proton which is present in the first. Yeah, hydrogen attached to sulfur. Because it is very acidic, so this base will attack on this particular proton, and you will have a anion at this sulfur position. So now what will next sulfur will do? See what you have ended up with this. Sorry. You have this negative charge here at sulfur, and you have this OTS. Now can anyone tell me what happens next? see what will happen next. This sulfur as a anion, and you have a leaving group here. It will attack on this carbon, and this leaving group leaves out. Now, what is the driving force for attacking of this particular carbon ion is, now you will end up having how many carbon number rings? 1, 2, 3, 4, and 5. Right? So the driving force for the particular reaction to take place is the generation of the five-membered ring. And I have told you, according to the base strain theory, five-membered ring is very much stabilized than six-membered ring, right? Because in the five-membered ring there is no torsional strain, there is no angular strain. This is which is present. But when you go to the six-membered ring, what happens? There is no torsional strain, but there is angular strain, right? So angle is getting deflected. So that's why whenever there is a possibility of forming five or six-membered ring, it is five-membered ring which is favorable. So because here also you have a five-membered ring formation tendency and a possibility of formation of the five-membered ring, that is why this carbon ion will go here and this leaving group leaves out to give you. Now what is the particular product you will have? Can anyone tell me out of these four which will be the second? Third one, right? So here how you are going to number it. See, this is a six-member ring which is already present. So this is the board shaped six-member ring. One, two, three, four, five, and six. Now what you have here is the five-member ring. Here, one, two, three, four, and five. A five-member ring is getting generated here. So this is how you will end up having a this product rather than a uncyclized product. Is it clear to all of you? Because you have a base in the system and you haven't added any acid, any protic solvent. That is why this cyclization is taking place. If you have added any of the solvent in this case, like ethanol, let's say, if you have added any ethanols in the case, it is a polar protic solvent, ethanol. So it will dissociate and will give you a H plus in the system. And now this H plus will take up by this sulfur anion. So there it will quench. Then it will quench and it will not going to give you the further cyclization. But here there is no solvent, there is no polar solvent that is present in the system. That is why the cyclization is very much facile than the protonation. So here that is why first is not the particular answer, because if the protic solvent is there then the protonation can be happen, but if the protic solvent is not there then how come the protonation happens? So that is why the cyclization is favorable. And here instead instead of being in the S minus and there also OH is OTS, right? This is why it is not that particular thing. And also this is not getting formed because OTS is a leaving group rather than the nucleophile. It is a leaving group. So that is why you cannot able to form this particular species. So the particular product which you will end up having is the option number 3. So is it understood to all of you, this question? Any doubts? If not, I am moving towards the problem number 10. Is it clear to problem number 9, guys? Okay. Then I'm going to problem number 10. So in the problem number 10 again, you have to answer the major product form in the following reaction. So I have explained you that MCPBA is a epoxidizing agent. So basically what will happen, epoxidation will take place. So if you have this alkene, the epoxide is getting formed. But now you have to assign the stereochemistry of that oxide as well. So if epoxidation is what taking place, then the option number 1 and option number 3 is getting neglected, right? So now among these 2 and 4 you have to answer. So now can anyone tell me which could be the possible answer among these 2 and 4? I have told you that this epoxidation is taking place like this mechanism. We have already talked about it. So you have two possibilities: either the epoxidation takes place on the below the side or above the side. So can anyone tell me which would be the possible answer, second option or the fourth? Option fourth. Anyone saying option second? Option four. How option four, guys? Yes. So this methyl group is above the plane and hydrogen is below the plane. So now there is a thing which comes into play, that is the steric hindrance. So if epoxidation has to happen, then it will prefer that side which is less sterically demanding. So it is the below the plane that is less sterically hindered because of the presence of hydrogen at that position. And if it goes above the plane, then this methyl is creating the steric hindrance for this oxygen. So that is why instead of second, you will have a fourth as a product, as a major product, because methyl is present above the plane, and due to the steric hindrance, epoxide wants to deliver from below the face. Is it clear the option number 4 is the correct one? How it is the correct one? Any query, any problem in this question? Any query, guys? Is it clear? Okay, then just respond now if it is clear or not. Okay, so I am thinking that it is clear. Then I am going to problem number 11. So again, a similar kind of question here. So here you have already the epoxide which you have made here now. They have used this epoxide here in this question, and they are asking what would be the major product for this reaction. So now here I have told you it is a strong base. Sorry, strong nucleophile. How? Sodium is getting a positive charge and sulfur is getting a negative charge. So it is behaving as a nucleophile rather than a base. So now tell me what could be the possible option for attacking of this nucleophile. There are two phases. Either it will attack on this phase, either it will attack on this phase. So now just tell me what would be the phase in which this nucleophile will attack. Backside attack from, yeah, second way. Because if it goes to the first way, then there is a steric hindrance again. This is a substituted side, and it will feel a steric hindrance from this side. And here there is no substituent or a hydrogen to interfere. So hydrogen is being a very small group. That's why this nucleophile wants to go from pathway 2. That is the carbon number second is getting attacked, and this CO bond is getting cleaved. So now tell me which is the correct answer in these particular four options. Option 4. Option 4. Is it really the option number 4? Because here sulfur is going through the second path. Option 3. See, you are ended up with this particular system. Let me write it so that it could be visible to all of you. Now, if the CO bond is cleaving from this side, you will have this OH, and C2 attack is going to take place from the nucleophile, And from the back side, I have told you, because it is substituted the front side, and here you have a methyl. So now tell me what is the correct option. What is the correct? Yeah, option number 1. How it is correct? See, guys, first of all, this nucleophile has to attack on the epoxide ring. I have told you previously that epoxide ring has a tendency to open up because of the ring strain. So that is why whenever you have a strong nucleophile in the system, it will definitely going to open your epoxide. So there are two options for this nucleophile to attack, either the carbon number 1, either the carbon number 2. So carbon number 2 is being getting attacked because carbon number 1 is facing the interference of this methyl group, but here only hydrogen is present, and here you are safe because steric hindrance is not there. So nucleophile prefer this side. Now, what is the reason for stereochemistry? Because this epoxide is above the plane, methyl is above the plane, so one face is blocked. See, if you see that basically at this carbon and at this carbon, if epoxide is there and it is above the plane, so one of the face is blocked already, so you don't have liberty for your nucleophile to come from above the place, because first above the place is blocked by epoxide, and also there is a methyl due to the steric hindrance. So here one face is blocked by the epoxide ring, so there is no option for your nucleophile rather to come from the opposite side of the epoxide ring. So to cleave this epoxide ring, it has to come from opposite side because one face is blocked. Let's see it like a chair configuration. So if it is there, it is kind of this. I'm not good with drawing, just adjust it. So here, if it is above the plane, guys, it is better visualized here. If it is above the plane, then your one face is blocked, the above the place is blocked. So nucleophile will seriously is going to have a very great amount of steric hindrance, and also it would not prefer this much energy to lose, and that is why your nucleophile will come from below the plane, because one face is although blocked. So this is how cleavage will happen, and you will end up having this SPH. So is it clear to all of you how the option number 1 is the correct one, how the stereochemistry is there, how the SPH is attacking on the carbon 2, not the carbon 1? Any problem, anything which is not clear? Okay. Then going to problem number 12. So problem number 12. So guys, they are asking the compounds that are aromatic are. So among these 1, 2, 3 and 4, you have to assign that which compound are aromatic. Which of the compounds are aromatic? So one by one we are going to these compounds. Just tell me the compound number 1. Is it aromatic, anti-aromatic or not? You don't have to worry about it. Just tell me, is it aromatic or not aromatic? How many pi electrons are there? Yes, anti-aromatic. How many pi electrons are there? There are 8 pi electrons. 2, 4, 6 and 8. So there are 8 pi electrons, and that is why we are saying that it is anti-aromatic compound, because it is conjugated cyclic flat having the 4 and pi electrons. So it is anti-aromatic. Yes. Now coming to the option number 2, tell me, is it aromatic or anti-aromatic? Aromatic. How? Because it is conjugated, it is having 4n plus 2 pi electrons. So the difference between these two is in the number of electrons only. So number of pi electrons in one is 8 pi and second is 6 pi. So that is why in the 6 pi you are having a aromatic species, whether rather in the 8 pi you are having the anti-aromatic species according to the rules. So now it is aromatic. So now coming to option number 3, is it aromatic or anti-aromatic? Aromatic. How? Because now you have to consider the lone pair of electron that is present on this oxygen as well. It is in conjugation, right? So if it is in conjugation, then it is also employing in the number of pi electron count. So how many pi electrons present in the system? 6 pi electrons. So if it is 6 pi electrons, then we have said that it is aromatic because it is conjugated, cyclic, flat, all the things are there. Now coming to this last. How many pi electrons? 10. So aromatic or anti-aromatic? Aromatic. So it is also aromatic. So just tell me the correct option then. I have told you which is aromatic, which is not aromatic. Which will be the correct option? Option number second. So 2, 3, and 4 are aromatic compounds, whether one is anti-aromatic. So is it clear to all of you how we have assigned aromaticity and non-aromaticity to these compounds? I think it is clear to all of you. If it is clear, then we are going to problem number 13, which is the last problem for this session, guys. So just have a quick look on it. So in this question, they are saying upon oxidation with the reagent X, 2-methyl propane 1,2-diol gives you 2-hydroxy 2-methyl propanol, and you have to identify the X. Basically, they are giving you a reactant, giving you a product, and you have to assign the reagent. Which reagent will undergo the conversion from this reactant to this product? So now coming to the structure of this reactant and product. So it is the 2-methyl propane 1,2-diol, the reactant, and 2-methyl 2-hydroxy propanol. So here, these are the four reagents which are present, and you have to tell me that which is the reagent X which is governing the oxidation. So now this is chromic acid, Jones reagent, PCC, LAH. So it is a oxidation. So just tell me which is the which could not be the possible answer. Which could not be the possible answer. See guys, here it is telling you that the oxidation is happening, but if you see, there is lithium aluminum hydride, and we have also talked about this reagent previously. So it is a reducing agent rather than the oxidizing agent. So it is a reducing agent. It will reduce, it doesn't oxidize. So that is why this option is getting eliminated, although, and you are ended up having this three options in hand. So is it the chromic acid, Jones reagents, or the PCC? And the condition is you have 2-hydroxy, first is primary and the second one is tertiary, and only one hydroxyl group is getting oxidized, whether your tertiary group is as it is. So now which particular reagent will give you this kind of selectivity? So can anyone tell me out of these three which could be the possible answer? Jones. What is Jones? Jones is CrO3 and H2SO4. CrO3 plus H2SO4. This is Jones reagent, right? And PCC is also chromic acid indicium. So now what is happening, guys? So here, if Jones reagent you have applied na CrO3 in H2SO4, then what happens? It will give you this alcohol, but there is oxidation, or you can say any other thing which is happening at this alcohol as well. You will have a very low yield if you say that you are using Jones reagent on this particular compound and you are getting this particular product. So it is not very clean reaction which is going, because Jones reagent you have CrO3 H2SO4. in that condition there is no leaving group or some kind of reaction which is happening. But if you see that in the case of PCC and BCM, what is happening? PCC is CrCO, basically this chromic acid. This chromic chloride is basically converting uh, into this aldehyde. How? This alcohol is getting oxidized to aldehyde by this PCC. So if you say this PCC, then it will react with primary and secondary alcohol. It has a selectivity that it will react with primary secondary alcohol. But for tertiary, it is not going to give you the reaction. So, tertiary alcohol is not going to give you the oxidation in the presence of PCC, but primary and secondary is giving you the oxidation in the presence of PCC. So, there is a clear cut selectivity which is arising in the case of PCC, which is not there in the case of Jones reagent. So, Jones reagent, the reaction is not going to give you the particular product very cleanly. It will form a multiple spots, and also the yield is very low. And I am not sure whether it will form or not, right? But with PCC, you have a clear cut selectivity in between this primary and tertiary alcohol. So, PCC will not oxidize the tertiary alcohol but will oxidize this primary alcohol. So, that is why the reagent which will be very much used for this kind of transmission, for this kind of oxidation, is PCC in DCM. Okay, so the particular answer for this compound, for this conversion, is the third option, PCC, pyridine dichlorochromate, and DCM. Is it clear to all of you why PCC is the required answer? This is the particular mechanism for PCC. Okay. So I hope it is clear to all of you today's lecture, and I'm just closing the session now. I'm done for today. So this is it for today, guys. What happened? Yes, tell me. You have raised the hand, right? Okay. So okay, so if there is no problem, then I'm closing the session. Thank you so much, guys, for attending the session, and you will get this video on the YouTube channel. You can go through it. If anything is not clear, then just comment in that particular YouTube channel only, because this is the last section for from my side for this course. So it is closed. So thank you so much for attending, and now I'm closing the session. Thank you so much. Thank you.